Okay, so now the next basic situation that we had here was situation number or activity number 3. It was activity number 3, and that was basically this activity. So we had activity number 3, and in activity number 3 what we did basically was that we threw a dice 20 times, and we noted down the number of times the numbers 1 through 6 came up, and we recorded our observation in the form of a table. So we threw a dice, so basically you can say throw a dice 20 times and record your observations. Meaning that how many times you get number 20, how many times you get number 1, how many times you get number 2, how many times you get number 3, and so on and so forth. And if you record your numbers in a table, and for example, if you take this ratio of the number of times 1 turned up, the number of times 1 turned up, divided by the total number of times the die is thrown, divided by the total number of times the dice is thrown, and again, if you do the same kind of thing, for example, the number of times 2 turned up divided by the total number of times the dice is thrown, and so on and so forth, all the way up to 6. And then we throw the dice 40 times, and instead of 20 times you throw the dice 40 times and record the observations and calculate the fractions as done here. And what you will see is that as the number of throws of the dice increases, you will find that the value of each fraction of such fractions basically gets closer and closer to 1/6. So you can say that as the number of times you throw the dice increases the fractions basically calculated above, the value of those fractions gets closer and closer, and closer to 1/6. And then it says that, for example, to see this, you can perform a group activity as done in activity 2. Divide the students in your class into small groups. One student in each group should throw a dice 10 times, and observations should be noted, and cumulative fractions should be calculated. And then the values of the fractions for the number 1 can be recorded in table 15.4. 15.4, this table can be extended to write down fractions for the other numbers also, and other tables of the same kind can be created for other numbers. So then you can create a table here, the total number of times the dice is thrown in a group, and then the cumulative number of ones, and then so on and so forth. So for example, if you want to, then again you can do this cumulatively and inside the group. And what you can do, for example, now this is just for number 1, then you can extend this to all the 6 numbers that you could get from a dice. So you could say that, for example, this is the group, this is the group number, meaning that you divide your class, for example, or basically the number of people that you have into different groups, and this is the group number, and over here you have the total number of times the dice is thrown in a group, the total number of times the dice is thrown in a group. And then you have the cumulative number of times one turned up, the cumulative number of times one turned up divided by the total number of times the dice is thrown. The total number of times the dice is thrown. So for example, this is just now for example for number 1, right? So then what you would do is that, for example, let's say that you have group 1, group 2, group 3 and group 4, and over here the total number of times the dice is thrown in a group is, for example, in this group we throw the dice 15 times, over here 15 times, 15 times and 15 times. Each group throws dice 15 times, for example. And then what we can do is that, for example, for the first group, the cumulative number of times, for example, one turned up, let's say that in 15 times is, for example, 2 times, for example, no, basically 1/6 of a time, 1/6 of the time. So 1 divided by 6 is basically 0.1666. So let's say that in this group it happens, for example, 2 times, for example 2 divided by 15. And then over here it happens, for example, basically in the first round that you get number 1 twice out of the 15 times. In the second round, let me write this way, so meaning that for the first round I'm getting two ones out of the total 15 times that I throw the dice. The second time I have the 2 15ths, and then I throw the dice another 15 times, and I get another 3 times here. So which is simply equal to, for example, 5 20ths. The third time for group 3, so I already have a 5 20ths there, and then I basically throw the dice another 15 times, and then I get another 3 times. I get another 3 times, which is basically 8 35ths. When it comes to when we get to group 4, I already have 8 35ths. I throw the dice another 15 times, and let's say that I get another 4 ones. and so I get, for example, 12, for example, 40/50ths. So as you can see here, 2/15 is the same thing as 0.113. This is the same thing as approximately 133. So 5/20 is the same thing as 1/4, so 5 divided by 20 is equal to 0.25. So this is approximately 0.25. 8/35 is the same thing as 0.228. 0.228. And 12/50 is the same thing as 0.24. This is approximately 0.24. Now 1/6 is the same thing as 0.16. So I might actually have I have made a mistake here. Sorry. No, I have made a mistake here. This is actually supposed to be 15. Because the value is not supposed to get above above 1/6. Okay, so basically for group 1 I have 2/15, right? So 2/15, and when we get to group 2, you already have 2/15. You throw the dice another 15 times, not 5 times, but 15 times. Let's say you get another 3 ones. So that's basically 5/30ths, which is the same thing as 5/30ths, which is the same thing as, for example, 0.167, approximately 0.167. And when it comes to the third group, you already have 5/30ths, and then you throw the dice another 15 times, and let's say that you get another 2 ones, which is equal to 7/45ths. Now 7 divided by 45 is equal to 0.155, approximately 0.155. And when we get to the fourth group, we already have 7/45ths, and I get to throw the dice another 15 times, and let's say I get another 4 ones, for example, another 4 ones. So that's going to give me 11 divided by, for example, 50/60ths. So 11 divided by 60 is equal to 0.183, approximately 0.183. Now, of course, the values that I chose here might not be very realistic, but 1 divided by 6 is the same thing as 0.166, 0.17. So the actual value of this probability should be something around. I mean, theoretically, it must be something around 1/6, which is 0.167, right? So we are getting some values around the same number over here, although over here we got a little bit above that number, but that's not that big a deal. Maybe this number is not very realistic, really, because 4/15 is the same thing as 4/15 is the same thing as that's much too high. That's much too high. That's basically why the value got all the way up to 0.183. Otherwise, we should Otherwise, if we are careful enough in choosing the values, we should remain somewhere around the same value, 0.16, 0.15, 0.14, and theoretically around 0.167, because the probability becomes 1 to 6, and 1 to 6 is basically 0.167. Okay. So this was basically this was basically situation number or activity number 3, and we had another activity over here which was activity number 4. And let's do this activity as well, because we might actually need these activities in the rest of this chapter, in the rest of the next chapter as well. So let me go over here, and now if basically the activity 4, basically what we have here is that what we did, we tossed 2 coins simultaneously. Tossed 2 coins simultaneously. 10 times, and record your observations. 10 times. So that's basically the experiment that we did. And then we had, for example, the number of times no head came up, the number of times one head came up, the number of times 2 heads came up, and so on and so forth. And we calculated the value of the observations there. And then we got some values here. So I'll keep this activity over here as it is, and I will not basically add or subtract anything to it. I'll just keep it as it is, and then we will know what to do with it later. And I will keep this basically this page along with the number. So this was in my book, it's 428. It's 428. So we can come back to this page anytime we want. And so now let's see what we have here. So it says that in our experiment, if our experiment was so we said that in activity 1, the getting of a head in a okay. So we talked about all of these things, and now we want let's consider some examples. So to start with, let us go back to activity number 2 and table 15.2 in column 4 of this table. What is the fraction that you calculated? So activity number 2, and in column number 4 of this table, basically what we calculated was 17 to, for example, it was 17 to 45. But it is the empirical probability in column 4 of this table. What is the fraction that you calculated? Nothing, but it is the empirical probability of getting a head. So basically over here I have a head. Basically this is the cumulative number of heads and the total number of times the coin is tossed. So what that means is that if you divide the cumulative number of heads, meaning that basically over here we got 3 heads over here, and we tossed the coin, for example, 15 times. By the second group we got another 15 heads. I'm sorry, we tossed the coin another 15 times, and we got another 7 heads. So if you add all of those together, you get 10 to 30. In the third group, we got another 7 heads, and we tossed the coin another 15 times, so we got 17 to 45. That means that we have, what we have done, we have actually, the total number of times that we have tossed the coin was 45 times, and the total number of times that we got a head was 17 times. So that's 17 to 45. So this is the empirical probability of getting a head. Note that this probability kept changing depending on the number of trials and the number of heads obtained in these trials. So of course this kept changing based on the number of trials that we had and the number of heads that we got in those trials. And similarly, the empirical probability of getting a tail is obtained in column 5 of table 15.2. This is the table that they're referring to. This is, for example, 12 to 15 to start with. Then 2/3, for example. 20 to 30 is 2/3. And 28 to 45, and so on. So the empirical probability depends on the number of trials undertaken and the number of times the outcomes you're looking for coming up in these trials. This is the number of outcomes you're looking for coming up. This is the number of outcomes you're looking for that come up in this total number of trials. And that's basically called the empirical probability of, for example, of getting tails, for example. So again, the empirical probability depends on the number of trials undertaken and the number of times the outcomes you're looking for basically come up in those basically number of trials. Now, we have another activity here that says that before going further, look at the tables you drew up while doing activity number 3. Activity number 3, which was basically this activity over here. So this is group 1 and this kind of table, I suppose. Find the probabilities of getting a 3 when throwing a dice a certain number of times. Also show how it changes as the number of tries increases. Let us consider some other examples. So that's not, since I don't have any values there, I don't want to confuse ourselves, so we can just simply move to examples. Let's see what we have over there. And we will keep this for future reference. So as an example, let's do an example here, and basically we had one definition here which needs to be remembered. So basically we said that, just to remind you of the definition of basically the empirical probability of some trials, it says that let n be the total number of trials, the total number of trials, the total number of trials, the empirical probability P of E, the empirical probability the empirical probability P of E of an event E happening, is given by P of E is equal to the number of trials in which the event happened, the number of trials in which the event happened and you divide that by the total number of trials. The total number of trials. Okay, so that is that. Okay, so now to do a couple of examples. So let's say that you have a coin is tossed 1,000 times. So you have a coin, you toss one, basically you toss a coin basically 1,000 times with the following frequencies. With the following frequencies. So we have heads 455, heads 455, and tails 545, which is 1,000 basically put together. Now you want to compute the probability for each event. So basically the probability of since the coin was tossed 1,000 times, the total number of trials is 1,000. So 1,000 is the total number of trials. Total number of trials, which is equal to 1,000, because the coin was tossed 1,000 times. Now let's call the events of getting a head and getting a tail as E and F. So basically E would be the event of getting a head, getting heads, or basically not a head, or let's call it heads, and F, I call it the event of getting tails, right? So then the number of times E happens, meaning that the event of getting heads, the number of times E happens, that is the number of times a head comes up is 145. The number of times basically a head comes up is 445, which is the number of times E happens, which we said that E was the event of getting heads basically. So that means that the probability of E would be equal to the number of times that E happens, which was 455, divided by the total number of trials. So the probability, so let me write it this way. So the probability of E is the number of heads is the number of heads to the total number of tries, to the total number of tries. So now I can write this as basically the probability of E. I can write it as P of E is equal to the number of heads, which is basically 455, as we saw over here. 455 divided by the total number of tries, which was 1,000, so that you can simplify to, for example, of course, that you can simplify to 0.455. Now the probability of the event of getting a tail, the probability of the event of getting tails, which is the same thing as, well, the probability of F happening, basically, would be the total number of tails, tails divided by the total number of tries, divided by the total number of tries, which is, then I can say that the probability of the event of getting tails, I could call it P of F, because I called F the event of getting tails, right? The event of getting tails. So P of F would be equal to the number of tails, which was 545 to the total number of tries, which was 1,000. So that's equal to 0.545. And as you can see, note that in the example above, P of F plus P of E, if you add these together, P of E plus P of F is equal to 0.455 plus 0.545, which is equal to basically which is equal to 1, simply 1, because we have 0.455 and 0.545, so you get a 0 over here, 1, 901, 0, 1, and 0, so that's a 1. That is a 1. So you can see that the probability of getting heads plus the probability of getting tails is equal to 1, and of course note that in this experiment that we are doing, that we are tossing this coin, there are only two different possibilities. There are only two possible events, either tails happening or heads happening. And then once you basically calculate the probability of each of them and add those two together, then that basically then those two numbers added together adds up to a 1. Now what's interesting is that, suppose that, for example, here we were talking about for example, throwing a dice. We were basically talking about throwing a dice. So now in throwing a dice, as opposed to having two different possible events happening, in throwing a dice we have basically the possible things that could happen. The possible outcomes would be basically getting a 1, the event of, I can call it the event of getting a 1, or you can have the event of getting a 2. That can happen as well. The event of getting a 3, the event of getting a 4, the event of getting a 5, and the event of getting a 6. There are 6 different numbers on the 6 basically faces of a dice. And I can denote these events by, for example, A. I can denote this by B. I can denote this by C. I can denote this by, for example, D, E, and F. Now, and then based on this, I can calculate, for example, P of A, the probability of A happening. I can in the same way that we did here. I can calculate P of B. I can calculate P of C. I can calculate P of D. I can calculate P of E. I can calculate P of F. And in this experiment, again, if you calculate P of A plus P of B plus P of C plus P of A, B, C, D plus P of E plus P of F, add all of these together, all the 6 possible outcomes of this experiment, calculate the probability of each of them happening, add all of them together, again you will get a 1. So meaning that basically the only 6 possible outcomes of this experiment are basically these 6 things happening. If you calculate the probability of them and then add those probabilities together, you will always get a 1. So, or suppose that, for example, you have basically 2 coins are tossed simultaneously 500 times. You have 2 coins are tossed simultaneously 500 times. So we get basically 2 heads, 1 head, and no head. 2 heads, 1 head, and no head. The number of times that these happened were 105 times and 275 times, and then you had also 120 times. Now if you add these numbers together, you will get, this is 2095, 100, and plus 400 is 500 times. That means that the only things that we got, 2 heads, 1 head. Okay. So now what you want to do here, you want to find the probability of occurrence. You want to find the probability of occurrence of each of these events, of each of the events. So each of these would be an event, and so we said that basically an event so basically to define an event, we said that so an event for an experiment is the collection of some outcomes of the experiment. an event for an experiment is the collection of some outcomes of the experiment. And of course, we will define that more precisely. So, but for now, let's just call this, for example, the event of getting 2 heads, for example, the event of getting 1 head, the event of getting no heads. And let's call this, for example, let's call the event, for example, let me be consistent with the book. So now what we can do is that we can denote the events of getting 2 heads, 1 head, and no head by E1, E2, and E3. So I can denote this as E1, for example, E2, and E3. So E1, for example, that would be the event of getting 2 heads. The event of getting 1 head, that would be E2, and the event of getting no heads would be E3. And so then the probability of each of these events happening would be, for example, P of E1, P of E2, and P of E3. So now the 2 coins have been tossed simultaneously 500 times. That means that the total number of times that the 2 coins have been tossed is 500 times. So basically, the total number of trials was 500 times. And the total number of times that we got 2 heads, that was basically 105 times. So that gives you, for example, something like 0.21. The probability of E2, which is the probability of 1 head, basically of getting 1 head. These are actually heads. 1 heads and 2 and no heads. So 1 head would be 275. So that would be 275 divided by 500, which gives you something like 0.55. And the probability of getting basically no heads, that would be E3. So P of E3, which is 120 divided by 500, which is equal to, over here, 0.24. So as you can see over here, 0.21 and 0.55 and 0.24, that's equal to 0.1, and then you have a 0 here and 1 here, and then 1 here, and the probability becomes 1. That means that these are the only, when you get a 1 over here, that means that these are the only possible outcomes of this experiment. And you can see, basically, you can see it over here as well, because when you toss 2 coins simultaneously, you have a coin 1 and a coin 2. The coin 1, the possible outcomes of coin 1 would be tails or heads. Coin 2 again would be tails and heads. Now you need to take the different combinations of these, of these 2 coins basically put together. You could get a tail and a tail. You could get a tail and a head. You could get a head and a tail. You could get a head and a head. So now, basically, the event of 2 heads happening would be all of such events. Basically, 1 head happening would be all of these 2 put together, all of such events. And no head happening would be this one, because there is no head here. So now we have actually covered all of the possible events of this experiment. And for the same reason, P of E1 plus P of E2 plus P of E3 is actually equal to 1. So that is basically that. And here it says that observe that P of E1 plus P of E2 plus P of E3 is equal to 1, and E1, E2, and E3, these three events cover all the outcomes of a trial. All the possible outcomes of a trial. Now, the next question that we have is basically example number 3. And that is, a dice is thrown 1,000 times with the frequencies for the outcomes 1 through 6 as given in the following table. So the dice, basically a dice has been thrown for basically 1,000 times. There's not 4, but 1,000 times. So now these are the frequencies that we have gotten. So we have the outcome here, and we have the frequency, and we have the frequency, and that is equal to, so for example, all the different outcomes were 1, 2, 3, 4, 5, and 6. And then you have 179, you have 150, you have 157, you have 149, you have 175, and you have 190. I think if you put these numbers, add these numbers together, you should get 1,000. Because you have a 1, 2, 3, 4, 5, 6, that's a 600. And then you have a 70 and 50 is 120, 120, 190, 190 plus 110, 190 plus 110 plus 90, that gives me 0, 18, 19, 390 here. And then you have a 9 and a 7 and a 9, so 18 plus 7 is equal to, you have an 18, you have a 7 there, and you have a 5 there. That's 15 plus 5 is equal to 20. 15 plus 5 is equal to 20, that's a 30. It doesn't make sense. Zero. No, that's not right. So you have 1, 2, 3, 4, 5, and 6. 6 times 100 is equal to 600. I'm counting these hundreds over here. And then you have 70, 50 is 120. Then 50 and 40 is 90. And 70 and 90 is 160. So you have 0, 15, 17, 1. That's 370. 370. And I think this is just something like 9 plus 7 is equal to 16. 16 plus 14 is equal to 9 plus 7 is equal to 16. And this is a 14, so that's 30. So that's 1,000. That is 1,000. Okay, so now, so that means that basically this dice has been thrown 1,000 times, and these are the frequencies related to each of the possible outcomes. Now you want to find the probability of getting each outcome. We want to find the probability of getting each outcome. Now, for example, the probability of getting a 1, so let's denote E of I, let E of I denote the event of getting the outcome I, where I is equal to 1 through 6. So let E of I denote the event of getting the outcome I denote the outcome of getting I, where I is equal to 1, 2, 3, 4, 5, and 6. Then we have, for example, the probability of outcome 1. Then we can write, for example, the probability of outcome 1 is equal to the same thing as the probability of E of I, which becomes E of 1, which is the frequency of 1, meaning that the number of times that 1 occurred or happened, divided by the total number of times the dice is thrown. Divided by the total number of times the dice was thrown. So what that means is that, for example, this is equal to 179 divided by 1,000. 179 divided by 1,000, which is equal to 0.179. And then we had, for example, then by the same logic, for example, P of E2 would be equal to, for example, 150 divided by 1,000, which is equal to 0.15. By the same logic, P of E3 would be equal to, for example, 157 by 1,000, which is equal to 0.157. And P of E4, for example, would be equal to basically 149 divided by 1,000, which is equal to 0.149. P of E5 is equal to, for example, 175 divided by 1,000, which is equal to 0.175. And finally, P of E6 is equal to basically 190 divided by 1,000, which is equal to 0.19. Now, if you add all of these numbers together, meaning that if you add all of these numbers together, we added all of these numbers together and we got 1,000, right? We got 1,000. So now, if the sum of all of those numbers, if basically I can call it sigma f of I, if sigma f of I is equal to 1,000, and now each of f of i's I have divided by 1,000, right? So that means that then sigma f of I divided by 1,000, as I goes from, for example, 1 to 6, that would be, for example, f of 1 divided by 1,000 plus f of 2 divided by 1,000. That gives me basically 1,000 sigma f of I, as I goes from 1 to 1,000. But of course I know that sigma f of I is equal to 1,000. That's 1,000th times 1,000, which is equal to 1. That means that if you add all of these numbers together, you would get a 1. And that means that then basically the probabilities of all of the different outcomes of the experiment, if you add them together, you would get a 1. So that is that. Now we have a couple more examples here, and of course we do need to do at least all of these examples, but then we will not go through the exercises. We will not go through the exercises, but since we need to be familiar with the concepts, we will do the examples and then we will go to the next chapter. So in the next video we will do the rest of these examples, so I'll see you in the next video. Thank you.